Water is being pumped out of a cylindrical tank at a rate of 10 cubic feet per minute. Now, the tank is a right circular cylinder, and it has a radius of 2 feet and a height of 5 feet. We want to know how fast the water level in the tank is falling when the water level is 4 feet. So I'm following the 4-step process that will work for solving any related rates problem. Let's follow those steps. You know, so many times I've heard students say, I don't know how to get started on a related rates problem. Follow this 4-step process. You'll be able to solve the problem. So write each rate in the problem as a derivative. So let's see, what are the rates in the problem? 10 cubic feet per minute. But how can I write that as a derivative? Let's see, cubic feet. Now that's volume, isn't it? And the minutes is time. So dV dt is, but now is this positive 10 cubic feet per minute or negative? Is the volume of the water in the tank increasing or decreasing? Well, it's decreasing because the water's being pumped out. So the derivative of volume with respect to time is a constant negative 10 cubic feet per minute. Are there any other rates in the problem? You know, sometimes I've heard students say, well, 2 feet's a rate or 5 feet's a rate. No, 2 feet is just quantity, right? 5 feet's a quantity. It's not a rate. You don't have feet per something, right? There is another rate in the problem, and it's the rate that we're trying to find. We want to know how fast the water level is falling. So we want to find how fast the water level is falling. So I need a variable to stand for the water level. So there's water in the tank. I need a variable to stand for the water level. Oh, why don't we just use H to stand for the water level? So I want to find the rate at which this water level H is changing with respect to time. Obviously, dH dt is going to end up being negative, right? Because the height is going to decrease. All right, step 2. I look at my derivative notation in step 1 and I identify the dependent variables. They're V and they're H, right? So I need an equation that relates V and H for the shape I'm given. And the shape's a right circular cylinder. So the volume of a right circular cylinder is the area of the base, which is pi r squared, times the height. Hopefully you remember that. But if you don't, you could Google area, or volume rather, volume of a right circular cylinder. So that's my equation that relates V and H. Now notice I've also got another variable R. Well, let's just leave that R for now. But that might be bothersome to us. We'll investigate that a little further in a minute. Step 3. Differentiate both sides of the equation from step 2 with respect to the independent variable time. Okay? So I just take my equation V equal pi r squared H. and I differentiate both sides with respect to time. Now, let's think about this R for a minute. This H is the height of what? This H is the height of the water. Now, I realize I'm given a height of the tank, right? The tank is 5 feet high. Okay, but the H here in my formula, V equal pi r squared H, that I'm concerned with, this H is the height of the water. And it's changing, right? It's a variable. It's not a constant. But now, how about the radius? Isn't the radius just the radius of the water here? The radius of the shape of the water? But the water conforms to the cylinder. The radius is just the radius of the tank. And it's not changing. The radius of the tank is not changing. It's a constant. Okay? So I can use constant multiple rule. The R is just like the pi from the standpoint of, in this problem, the R is a constant because the radius of the cylinder is not changing. So constant multiple rule, the pi r squared is a constant, so it comes out front. Multiplied by the derivative of H with respect to T. So notice, I've got an equation now that relates the two derivatives in step 1. Derivative of volume with respect to time, derivative of height with respect to time. Step 4, substitute values into this equation now that I've got from step 3 and solve for the requested rate. The requested rate is dH dt, right? So I'm just going to take dV dt equal pi r squared dH dt. dV dt I know is negative 10 cubic feet per minute. The radius is what? The radius is 2 feet. And dH dt is what I'm trying to find. So I solve for dH dt. And I get negative 10 over 4 pi. And that's feet cubed per minute over feet squared, isn't it? Let's stop and make sure that's correct. To solve for dH dt, I just divide both sides by pi times 2 feet quantity squared. So I take negative 10 cubic feet per minute, and I divide by the 2 feet quantity squared is 4 square feet times pi. Okay, now let's see if the units are going to work out right. Cubic feet per minute divided by square feet is going to give me feet per minute. Is that appropriate units for the derivative of height with respect to time? Minutes is a unit of time. Feet is a unit of height. Yes, our units are working. And so I really get negative 5 over 2 pi feet per minute. Notice our answer is negative, as it should be, since the height is decreasing. Now, there's a little situation about semantics here. The question is asked, how fast is the water level falling? So the water level is falling at a rate of 5 divided by 2 pi feet per minute. Notice I said positive 5 divided by 2 pi feet per minute. That's the rate at which the water level is falling. However, the derivative of h with respect to t is a negative 5 divided by 2 pi feet per minute, since the height is decreasing. I would not want to say the water level is falling at a rate of negative something feet per minute, because if something is falling at a negative rate, it would really be rising, wouldn't it? You've just got to watch the language of how the question is worded. Now, one thing about this problem, going back to volume equal pi r squared times h. When I took derivatives of both sides, what if I had used product rule here? What if I did use product rule? Okay? This is going to make this a little messy, but I'm going to write this anyway. If I had used product rule, I would have gotten dv dt equal pi, the first, so it's r squared times the second dh dt, plus the second h times the derivative of the first. That would be 2r dr dt. If I had not realized that that radius was a constant, I would have needed to use product rule. So the product rule is the first, r squared, times the derivative of the second, plus the second, h, times the derivative of the first. So the derivative of r squared with respect to t, remember r is a function of t, so this is really a composite function. The derivative of the outside is 2r. The derivative of the inside is dr dt. Now, when I go to simplify that, what's dr dt? See, I'm given dh dt, right? In the problem, look back at step 1. Well, I'm not given dh dt. I'm trying to find dh dt. And I'm given what? dv dt. But I don't know dr dt. What am I going to do with that? Oh, don't I know dr dt? I have to realize the radius of this circular cylinder, the radius of the water, is a constant. I have to realize that at some point in time in this problem. If I realize it early on, I don't have to use product rule here. But if I didn't realize that r was a constant early on, I would have had to have used product rule, but I've eventually got to realize that. And hopefully I'd be forced to realize that when I have to put in something here for dr dt. And the rate of change of the radius with respect to time is 0, since the radius is a constant. And so I get dv dt is pi r squared dh dt, which is what I had before.